By the end of this lesson, you'll be able to define rectification, explain half wave and full wave rectification, explain the smoothing or filter capacitor action, and describe voltage multipliers. Rectification. Most of the electronic devices used in our homes use alternating current. However, some of these devices like computers, laptops, and so on must convert the alternating current into direct current before they can be powered. A combination of several components like the transformer, a capacitor, and several diodes form the essential components needed to achieve such rectification. And so the diode converts an AC to a DC. So rectification is the process of converting an alternating current, which can be shortened as AC, into a direct current, mostly shortened as DC. So just note that from this topic onwards, when I say AC, I'm referring to an alternating current. When I say DC, I'm referring to a direct current. Now, the diode converts an AC to a DC. The components required to achieve rectification are the transformer, you also need a capacitor. You also require several diodes to achieve rectification. The diode converts the AC to DC. The transformer reduces the high AC voltage to a low AC voltage. Then the capacitor filters pulsating this to pure DC. A PN junction diode allows electric currents in only the forward bias mode and blocks electric current in the reverse bias mode. The diode allows current flow in only one direction. The diode therefore acts like a rectifier. The electric current produced in a forward bias condition is known as the majority charge carrier current, since it is majority charge carriers that produce the electric current in the forward bias mode. A DC produces current which flows in only one direction, and DC produces current which flows in one direction. Just by way of review, you have the current here and the time here. So you see that this is your positive end and this is your negative end. You see that if this is positive, it goes positive throughout. Let's look at an AC. An AC produces current whose magnitude and direction varies periodically. So if we had to draw a graph of an AC, so this is my current axis, my time axis. So you see that it's my positive side. Constantly, its polarity varies. At one point it is positive, the next point it is negative. As time increases, you see that its magnitude and direction varies. Let's note something over here. Now, the upper half cycle is called the positive half cycle, and then the lower here is called the negative half cycle. So in our subsequent topics, if I mention the positive half cycles, note that I'm talking about this from this axis upwards. The negative half cycle is from this axis downwards. That's for an AC. When an AC is applied to a PN junction diode during the positive half cycle, the diode is forward biased, allows current to pass through it. However, during the negative half cycle, the PN junction is reverse biased and does not allow current through it. So at this point, at the positive half cycle, the AC is forward biased, and the negative half cycle, it is reverse biased. This is our alternating current. We see that these are the positive half cycle. From here to here is our positive half cycle. Here to there is our negative half cycle. When it is in the positive half cycles, it is forward biased. When it is in the negative half cycle, it is reverse biased. We also mentioned that in the positive half cycle, current flows the negative half cycle, the current is blocked. So after rectification, the PN junction acts as what we call the rectifier. After rectification, it is observed that all the negative half cycles are blocked and the positive half cycles remain up there. This is what we call the pulsating DC, because you see that 1 minute it is up, the other minute it is at the mean position. 1 minute it is up, the other minute it is at the mean position. So we call it a pulsating DC. The DC produced from the diode is not a pure DC, in the sense that it is pulsating. I mean, your normal DC, you would expect that it will be a straight line, current, time. But this time you see that it is pulsating, but it is still a DC. So a pulsating DC is one whose value changes over a short period. Pulsating DC is one whose value changes over a short period, but the polarity remains the same. Now let's look at types of rectifiers. There are two types of rectifiers, namely the half-wave rectifiers, secondly the full-wave rectifiers. Let's look at the half-wave rectifier. A half-wave rectifier is a type of rectifier which allows only a half cycle, either the positive half cycle or negative half cycle of the AC signal, whilst the other half cycle is blocked. A half-wave rectifier is a type of rectifier which allows only a half cycle, either positive half cycle or negative half cycle of the AC signal, whilst the other half cycle is blocked. So in our earlier diagram, we had an AC. You see that before the AC entered the diode, it had both cycles complete, but after passing through the diode, it was left with just the top. You would see that the negative half cycle has been cut off, leaving just this. The reverse could also occur, where the positive half cycles are blocked and all that is left will be your negative half cycle. And so that is a typical behavior of a half-wave rectifier. A half-wave rectifier will not allow both positive and negative half cycles at the same time. Only one half cycle is allowed. Only a single diode is used to construct a half-wave rectifier. A half-wave rectifier is made up of an AC source, a transformer, mostly a step-down transformer, then a diode, and a resistor, or sometimes it's called a load, or sometimes called a load. The diode is placed between the transformer and the load. So this is a half-wave rectifier. This is our AC input. This is our transformer. This is our diode, our resistor, and then output. So after current has passed through the transformer, it is the AC input here passes through the transformer, passes through the diode, then it creates a pulsating AC. Now it is not palatable to have pulsating DC as an output to be used in machines, so it becomes very necessary to remove the ripples out of the output DC. These are called ripples because they go up, down in that manner. So it is very important that we will remove the ripples. In order to filter the pulsating DC, you would have to add what we call a capacitor. This is a typical half-wave rectifier with a capacitor. This is our AC input. Our transformer is here, our diode. You will notice that the output is such that the ripples have been removed. This is the initial pulsating DC, but after having been passed through the capacitor, you will notice that the ripples have been removed to a substantial amount. A filter converts the pulsating DC to pure DC. In this case, our filter is the capacitor. The capacitor is used as the filter to smoothing the pulsating or the ripple DC to pure DC. Okay, so this is what the capacitor does. It helps to remove the ripples or to suppress the ripples in the pulsating DC in the process, giving you what we call a pure DC. Let's move on to some advantages of a half-wave rectifier. One, it is easy to construct. All you require, you would see as we look at the other types of rectifiers that they require more components. All you require in a half-wave rectifier is a diode, you require transformer, you require a load, and you have a rectifier. Okay, you don't require an AC source, you don't require too much, so it is easy to construct. Number two, it is cheaper to construct. It is cheaper to construct. Does it have any disadvantages? Yes, it has disadvantages. So part of its disadvantages is that it produces very low output voltage. It produces very low output voltage. Number two, there is loss of power. Since the half-wave rectifier allows 1/2 of the cycle and the other half of the cycle is removed. Power is lost. You put in a wave or you put in an AC signal that has both positive half cycles and negative half cycles into a system, and then at the end of the day it comes out as only positive half cycles or negative half cycles. The other half cycle has gone to waste, and so there is loss of power. Our third disadvantage is that the DC produced is not pure DC, but a pulsating DC, which is not much useful. So they are not efficient AC to DC converters. So the DC that it produces at the end of the day is a pulsating DC, and nobody really requires a pulsating DC in their system. It's not really efficient, which is why the filtering action has to happen, which is why you have to add a capacitor to the entire circuit in order to obtain a pure DC. Now let's move on to look at full wave rectifier. A full wave rectifier is a type of rectifier which converts both half cycles of the AC signal into pulsating DC. In the half wave rectifier, you notice that only one half cycle comes out, so the other half cycle is wasted or is cut out. So what the full wave rectifier does is to give you the full benefit of both half cycles. Okay, so a full wave rectifier is a type of rectifier which converts both half cycles of the input AC signal into pulsating output DC signal. There are two types of full wave rectifiers. We have the center tapped full wave rectifier and the full wave bridge rectifier. Let's look at the center tapped full wave rectifier. This is the center tapped full wave rectifier. It has two diodes, one load over one resistor or load, a transformer. You have your AC input here and your DC output. Now we call it center tapped. You can see where the center tap is in the middle of the transformer. This is your primary winding, and then your secondary winding. So a center tap full wave rectifier is a type of rectifier which uses a center tap transformer and 2 diodes to convert the AC signal into DC signal. The center tapped full wave rectifier, let's look at the components. It's made up of an AC source, 2 diodes, a load or resistor. I would want you to note that the components of each. Remember what the components of a half wave rectifier. Now, this is that for a full wave rectifier, specifically a center tap full wave rectifier, then a center tapped transformer. So these are the components of the center tapped full wave rectifier. Now, let's look further at what happens in there. When the input AC is applied, the secondary winding of the transformer divides the input AC signal into 2 parts, that is positive and negative. Now both diodes D1, both of the diodes D1 and D2 allows current flow in the same direction. Current that flows in one direction constitutes a direct current, you remember. So the resultant current at the load or at the output is a direct current. The DC that appears at the output for each diode is a pulsating DC. What we are trying to say is that, see, if this one is, so if this very one, the diode 1 would give you current flow in one direction, which is a DC. This will also give you current flow in one direction, which is also a DC. So at the end of the day, it takes advantage of both diodes to ensure that you have the full complement of the wave. Now, what will a waveform of a center tapped full wave rectifier look like? This is a waveform of a center tapped full wave rectifier. Diode 1 looks like a half wave rectifier, if you remember the waveform. So up here, a ripple down there. Then diode 2 does same, only that it does it for the reverse direction, and so it takes advantage of this. Now because both of them come out at the output together, you'd see that it makes use of all, and so no power is lost in the scheme. It comes out as a pulsating DC. The advantages of center tap full wave rectifier. It has low power loss since no signal is wasted. 2, it has higher rectifier efficiency. Remember when we talk about the rectifier, the diode is acting as a rectifier in this case. Then third advantage, the output DC signal in full wave rectifier, specifically the center tapped, has fewer ripples than the half wave rectifier. Disadvantages. Now let's look at disadvantages of the center tapped full wave rectifier. Because of the components that go into it, you notice that you use more components than you would use for a typical half wave rectifier. So it has a high cost, or it is expensive. 2, it occupies a large space. At the end of the day, the output you get for a center tap full wave rectifier also comes as a pulsating DC. So once again, we would have to apply a filter in order to remove the ripples and make it a pure DC. This is a typical center tap full wave rectifier with a filter. These are your 2 diodes. This is your transformer. So a capacitor has been added to the load. So you see that what it has done is that it has removed the ripples. It has suppressed the ripples and giving you a pure DC output instead of a pulsating DC output. So a filter made up of a capacitor and a resistor is known as a capacitor filter. Okay, it's known as a capacitor filter. Okay, so that is it for center tapped full wave rectifier with filter. Let's look at the bridge rectifier. Now, what advantage does a bridge rectifier have over a center tapped full wave rectifier? The center tap transformer used in it is expensive and occupies a lot of space. So the major drawback is that the center tapped transformer used in the center tap full wave rectifier occupies a lot of space and it is expensive. So it occupies space, it is expensive. So then another type of rectifier has to be developed that will help solve this problem. And so the bridge rectifier comes into the question. So you see that for the bridge rectifier, there is no transformer. In its place, 2 extra diodes have been introduced into the system. And so a bridge rectifier is one which uses 4 or more diodes in a bridge circuit configuration to convert the AC signal to a DC signal. So in a bridge rectifier, a center tap transformer is not needed. So in this type of rectifier, a center tap transformer is not needed. A bridge rectifier. Now let's look at how it operates. The input AC signal from here applied across A and B, and the output DC signal is so you can see your input AC signal is applied across A and B, and your output DC signal is obtained across the load C at C and D at those terminals. The 4 diodes are arranged in series with only 2 diodes allowing electric current during each half cycle. Okay, so you can see they are in series, and 2 of the diodes allow electric current during each half cycle. They occur in a particular order. D1 and D3 are taken as a pair. So D1 and D3 are taken as a pair, and they allow electric current during the positive half cycle. So D1 and D3 are taken as a pair, and they allow electric current during the positive half cycle. Now D2 and D4 are also taken as a pair, and they allow electric current during the negative half cycle. Okay. When the input AC is applied across the bridge rectifier, during the positive half cycles, D1 and D3 are forward biased and allows electric current to flow, whilst D2 and D4 are reverse biased and blocks the flow of electric current. During the negative half cycles, D2 and D4 are forward biased and D1 and D3 are reverse biased. A bridge rectifier allows current during both the positive and negative half cycles of the input AC. So 2 things happen when an AC is applied across the bridge rectifier. Now, during the positive half cycle, D1 and D3 are forward biased, so electric current will flow. Then D2 and D4 will be reverse biased, so electric current will not flow. During the negative half cycle, D2, D4, D1, D3 change position, so negative. During the negative half cycle, D1, D3 now become reverse biased, meaning that no current will flow there, and then D2 D4 become forward bias. Note how the exchange takes place. Now, what will a waveform of this look like? This is a typical waveform of the bridge rectifier. This is our input AC. Now, D1, D3. Okay, remember we said in the positive half cycle, D1, D3 are forward bias, so current flows. So clearly you can see that D2, it means that D2 and D4 will produce no current in this positive half cycle. Now, in the negative half cycle here, you notice that D1 and D3 are now blocked, so you can't see anything here. But D2 and D4 are now producing current, so in that direction. When you combine these two, your total DC output will be a combination this. So you are going to have such a waveform. But once again, the total DC output is pulsating, has ripples, and so the ripple has to be removed. So then it can be removed once again by using a filter, your capacitor in the circuit. The advantages of a bridge rectifier is that one, there are low ripples in the output DC signal. Two, there is very high rectifier efficiency. Now let's look at some disadvantages. One, it looks very complex. I think by looking at it, it should be the very first disadvantage that comes to mind. It looks very complex. It is actually very complex. Two, more power loss as compared to the center tapped full wave rectifier. Now, in order to remove the ripples so that you have a pure DC, you would have to introduce a filter. Now, the bridge rectifier gives you a pulsating DC output that contains small ripples. These small ripples can be reduced if a filter is used at the output. In this diagram, this is the circuit diagram for a bridge rectifier with a filter. A capacitor is connected across the load or the resistor. This is the bridge rectifier, and this is your AC source. This is your capacitor resistor. What happens is, once again, that you can see that this is the waveform when a capacitor is used to filter it. Now, this is the waveform without the capacitor. You can see the ripples in it, but now the ripples have been suppressed. Those have been very much suppressed. Voltage multiplier. A voltage multiplier is an electronic circuit that delivers output voltage whose peak value is 2, 3, or more times greater than the peak value of the input voltage. So that's just like the name suggests, it multiplies the voltage. So it will give you an output voltage whose peak value is sometimes 2 times, or sometimes 3 times, or more times. It can be 4 times greater than the peak value of the input voltage. Now, what it does is that it converts a low AC voltage into a high DC voltage. It converts a low AC voltage into a high DC voltage. It is an AC to DC converter made up of diodes and capacitors that produce a high DC voltage output from a low AC voltage output. Now, the use of a voltage multiplier circuit reduces the size of the high voltage transformer and makes it possible to remove the transformer. So if I have a voltage multiplier in my circuit, it makes it possible to remove the transformer. So instead of putting a transformer which will step up my voltage, I can comfortably go and bring a voltage multiplier which will perform the same function. The voltage multiplier is made up of capacitors and diodes that are connected in different configurations. Voltage multipliers has different stages. Each stage is made up of one diode and a capacitor, so they come in pairs. If I have a capacitor, I have a diode. So it is not possible to find a diode and no capacitor. They come in pairs. Now, types of multipliers. There are 4 types of voltage multipliers. We have 1, the half wave voltage doubler, 2, full wave voltage doubler, 3, voltage tripler, and finally voltage quadrupler. Let's first look at the half wave voltage doubler. Now this is your half wave voltage doubler. It consists of 2 capacitors, 2 diodes, and your AC source. So come in pairs: capacitor diode, capacitor diode. So a half wave voltage doubler is a voltage doubler whose output voltage amplitude is twice that of the input voltage amplitude. So you put in just, so whatever you put here, it doubles it twice. It is made up of 2 diodes, 2 capacitors, and an AC input voltage source. Okay, an AC input voltage source. At this point, we want you to be able to identify a half wave voltage doubler when you see it. Not at this level, the details of the detail you are spared its complexities, but when you see a half wave voltage doubler, you should know what it does. What it does is that it increases your input voltage to twice, and gives you an output that is twice the input voltage. Let's look at the advantages of the half wave. The advantages: 1, high voltages are produced. High voltages are produced from the low input voltage source without using expensive high voltage transformer. Okay, so I can increase I can get my high voltage without having to go for an expensive transformer. Now the disadvantages: large ripples as unwanted fluctuations are in the output signal. So once again, ripples are present in the output signal. Now let's look at the full wave voltage doubler. The full wave voltage doubler consists of 2 diodes, consists of 2 capacitors, and an input AC source. Though it contains the same number of components as the half wave voltage doubler, you can see that the difference is in how the components have been arranged. Compare the 2 components. It also doubles your voltage input. So it is called a full wave voltage doubler because one of the output capacitors, one of these output capacitors, this or that, is charged during each half cycle of the input voltage. Let's look at the voltage tripler. It consists of 3 capacitors, 3 types. So the total output, you can say 3. What it does is that it increases your input to 3 times the, so it gives you an output that is 3 times the input. So the total output voltage is 3 times more than the applied input voltage. Let's finally look at the voltage quadrupler. It can be obtained by adding, can say what we just did was we just added one more diode capacitor stage to the voltage tripler circuit. So it can be obtained by adding one more diode capacitor stage to the voltage tripler circuit. So you just take the voltage tripler circuit and then add one more diode capacitor, and then you have a voltage quadrupler. Now the total output voltage of a voltage quadrupler is 4 times more than the applied input voltage. So the total output voltage is 4 times more than the input voltage. So an input V equal to Vn is put in here, you get an output of V not equal to 4 Vm. Let's conclude by looking at the advantages of voltage multipliers. One, they are applied in particle accelerators. They are applied in cathode ray tubes, called CRTs. They are applied in oscilloscopes. They are applied in photocopy machines. They are applied in power supplies. And finally, you can use them in X-ray systems.